Hi, I'm Darren and welcome to Level Up EE Lab. Well, it's high time I got back on my HF transmitter project, and that's the subject of today's video. I'll be going through the audio board that I built and tested, and this will be a great opportunity to show the Heathkit AV3 that I recently repaired. Let's get to it. Well, here I go again, making yet another circuit board. I pretty much got the process down pat now, including the chemical tin plating. And this guy is pretty small, 27 by 42 millimeters. And single-sided is fine, it's only audio frequency signals. Here it is all populated. It only took about an hour to build up. I did have to put in some jumper wires. There were two connections that couldn't be made on the copper side. But other than that little workaround, the rest of the assembly is pretty conventional, mostly 0805, SOT23 and other SMT parts, plus a few through-hole electrolytics. So next up is to apply power and signals and check it out. Alrighty, I'm in the lab and I've got the audio stage hooked up on the breadboard down here and a whole bunch of other equipment connected to it, and kind of cut to the chase, it's working. And I thought I'd demonstrate some of the more interesting features to measure on this stage. And in order to make these measurements, this is why I've got all this equipment. So let me explain what I've got. I got the Heathkit power supply providing the 12 volts. I do have the meter set on ampere or milliampere, I guess would be a more accurate mode. That's always a good practice when you're working with an unknown circuit after you get the voltage dialed in, to keep an eye on that current. Maybe not so much for this stage, but other stages, if you see the current start to drift, that can be an indicator that there's something wrong with your board and you need to shut it down, something's malfunctioning. As far as the rest of the equipment, of course, I got the Simpson as this Simpson signal generator as the input. It's on channel 1 of the 2465. That's this trace right here. Channel 1 is set to 5 millivolts per division, so we're looking at a signal that's 5 millivolts peak, or 10 millivolts peak to peak. And then on the output side, I've got a couple of things. I've got my basic multimeter set up on frequency mode, just so I can have an additional referee to know what the frequency is and see it very quickly. So I'm just under 500 hertz. And then, most interestingly, I have my recently renovated Heathkit AV3. Now, I did a whole series on this guy and brought it back to life, and this is the first application where I'm using it for a practical purpose. It's on the output, and it's monitoring on the 1 volt scale around 350 millivolts. So if you do the math, and channel 2, I should say, on the 2465, that's also the output. That's the larger signal. That's 200 millivolts per division. So we're looking at a signal there. It's about 520 millivolts peak. Now, for a pure sine wave, if you multiply that peak by 0.707 will give you the RMS value, and that's what this meter's reading is RMS. And 520 millivolts times 0.707 is 360 millivolts, and that's pretty much exactly where I am. Next thing I want to look at here, and it's a pretty simple measurement, is what is the gain of the audio stage. If you recall from the LT Spice simulations that I did in an earlier episode, all the stages combined worked out to be just about 40 dB of gain. Now, if you look at what I'm showing on screen right now, I've got roughly 5 millivolts peak coming in, and I've got roughly 500 to 520-ish, depending on how you want to eyeball that scale, output millivolt peak. And doing the quick math on that, just say rough and tough, that's a difference of 100 times, and do the logarithmic calculation, that works out to be 40 dB. So no big surprise, the board is working right to spec for what it should for gain. The next performance parameter to look at here would be the cutoff frequency of the low-pass filter. If you remember from the design calculations and then also what I verified in LT Spice, the cutoff frequency, or the minus 3 dB roll-off of that low-pass filter, is 1.125 kilohertz. And what I can do here is adjust the Simpson signal generator and actually see what that point is. And this is also an excellent example of where this AV3 will come in handy, because it has that dB, the decibel scale, right here in red. So what I can do is I can increase the output of the signal generator to put it at the 0 dB mark. And there's plenty of headroom in this audio board. I checked before I did this video, and I'm nowhere near the gain compression limit of this amplifier. And that's always important when you're doing a test like this. You don't want to be driving the amp into non-linear region. So I'm definitely still in the linear region. So once I hit it at 0, then I'll increase the frequency so that I can actually see where that needle will drop from 0 to -3 dB, and I can read the frequency here, and that'll tell me what my 3 dB roll-off point is. Now, I have reset the scale on the 2465 for the second channel. It's 500 millivolts per division, just so we don't see the channel 2 just go off screen. So here we go. I'm going to increase the amplitude next until I get to 0. Okay, that's pretty close. And then now I'm going to increase the frequency and watch for that needle to drop to -3. So that's pretty close, within an eyelash or two on the scale here. And I'm reading 1.115 kilohertz on frequency. So that's pretty much spot on. No big surprise. Low-pass filter design with op-amps is pretty easy and pretty straightforward, but it's always good to get a lab measurement to confirm that the circuit is working the way you designed it. All right, I had to do a quick battery change on the ZV-1. Folks like me that have had these cameras for a while learn pretty quickly that the batteries just don't last very long in these, and you got to keep several on hand, and of course that means changing the camera setup, so no big deal. Back and working here. Now, the low frequency response is just as easy to measure as the high frequency. You just turn the dial the other way is really what it comes down to. It's usually not that much of an interest with an audio stage like this, but just good to measure it while I have it set up. So same principle. I set the input signal so that I'm at 0 dB on the Heath kit, and I'll drop the frequency until I get to -3 dB, and we'll see what the frequency is on the meter. Here we go. All right, little bouncing going on there, but I think I'm pretty close. So the meter is showing just under 50 hertz, and the simulation predicted 40 hertz. No big deal. We're off by 10 hertz, but that's down into the barely audible region. But it's a measurement that you can make just to show that the circuit's working the way the prediction said it would. For the final test, I'm going to hook it up to my PG48 mic to check out the sound quality. Here I've set up split screen in Audacity so we can see as well as hear the difference between my standard audio recording technique and the audio coming out from this audio board. The screen on the left is what you're hearing now. It's my typical audio from the PG48 going into my home-built preamp, and after I apply noise reduction, compressor, some amplification, and a click remover filter. The screen on the right, which I'll play in a moment, is the audio from the audio board with only a noise filter applied. There was some 60 Hz ground loop hum that was annoying me, so I removed it, but that's the only manipulation I did to the audio. Notice right away the difference in the two spectrograms. There's definitely significantly less mid-frequency energy in the audio and very little high-frequency energy. Let's take a listen. Alrighty, I've connected my Shure PG48 microphone to the input of the audio board and connected the output to my sound card on my laptop, and this is what it sounds like. Not surprisingly, that low-pass filter is knocking out so much of the high-frequency components that my voice definitely sounds like it'd be coming from an AM or a single sideband reception. So this audio board should work just fine. If you recall, a single sideband transmission is limited to around 3 kilohertz, give or take, bandwidth anyway, so knocking out those high-frequency components is exactly what I needed to do here. Now, I'm not really planning to use this PG48 microphone with this transmitter. The reason I used it for this video is to have a known standard to compare the performance of the audio board to something that I already know well, and that's the audio that I make for these videos. Now, the design of this audio board is compatible with a wide range of impedance microphones, including condenser mics, and I do have several of those handy, and that's probably what I'm going to end up using. Alright, so let's take another look at the block diagram and see what's up next, and I'll put it up on screen here for reference. At this point, I've completed the audio amplifier and the low-pass filter, which means the next stage is the balance modulator. That's where the signal, of course, is going to get shifted up in frequency to the 5.5 megahertz double sideband suppressed carrier that I'll need to eventually transmit on the air. So that stage will be the subject for the next video. As always, I hope you're enjoying these multi-part series that I put together on a complex project like this. And of course, if you have any questions or comments, leave them in the section below. Thanks very much for watching, and until next time, bye for now.